Dear students, in this video lecture I am going to discuss about the non-destructive testing and high voltage sharing breeze. So first of all we will discuss what is the necessity of non-destructive testing, then we will discuss about what is dielectric loss and how the dielectric loss is calculated in case of dielectrics or insulating materials, and the dielectric loss depends upon which factors. Then after that we will discuss high voltage sharing breeze. Now first of all, what is non-destructive testing and what is the necessity of non-destructive testing? So actually all electrical apparatus or the equipments are insulated with either gaseous or liquid or solid insulating materials. The insulation is provided between the live parts and the grounded part of the equipment. The insulating materials are subjected to various high voltage tests, but the disadvantage of performing the high voltage test is that during the process of high voltage testing, the equipment may be damaged if the insulation is if the quality of the insulation is not good or faulty. So for this reason, non-destructive testing methods are used, and that will permit early detection for the insulation faults. So in short, to test the quality of insulating material and to assess the electrical properties, for example DC resistivity, dielectric constant. Dielectric constant means permittivity, then loss factor or dissipation factor, non-destructive testing methods are used. So various non-destructive testing methods are used to test the quality of the insulating material and also to assess the electrical properties of insulating materials without performing the high voltage test. Now the first is measurement of the insulation resistance under DC voltages, then determination of the dissipation factor or loss factor 10 delta and the capacitance C of the insulating materials, then measurement of partial discharges. Now coming to the dielectric loss, what is dielectric loss? So actually when the AC voltage is applied across the insulating material or dielectric, then some of the electric energy is absorbed by the insulation and dissipated as heat. So the energy absorbed, this energy absorbed is called what? Dielectric loss. So when the insulating material is subjected to AC voltage, the leakage current, that means the current I, does not lead the applied voltage by exactly 90 degree. The phase angle phi is always less than 90 degree. The dielectric, so you can see the current I does not lead the applied voltage by exactly 90 degree because of what? Dielectric loss, right? So it is always less than 90 degree. So V is equal to the applied voltage, then C is the capacitance of the dielectric or insulating material, phi is the phase angle between voltage and the current, and it is also called the power factor angle of the dielectric or insulation, and delta is the loss angle of the dielectric. Then so you can see the charging current is equal to V upon Xc, so is equal to omega CV. Then how to calculate the dielectric loss? So dielectric loss per phase is equal to Vi cos phi. Now here phi is equal to 90 minus delta, and therefore we can write Vi sin phi. So and therefore the dielectric loss, you can see the dielectric loss per phase is equal to omega. Omega means 2 pi f. F is equal to frequency C V square 10 delta, where F is equal to frequency, C is nothing but the capacitance of the dielectric or insulating material, V is equal to the applied voltage, and 10 delta is called the loss factor or dissipation factor. So you can see the dielectric loss is directly proportional to 10 delta. So 10 delta means the loss factor or dissipation factor. So the value of this 10 delta for the insulating material should be as low as possible in order to reduce the dielectric loss. So you can see the dielectric loss P is equal to 2 pi f C V square tan delta, and the value of delta should be tan delta should be as low as possible. And for good insulating materials, the value of tan delta may be between 0.0001 to 0.0001. Now coming to the high voltage Schering bridge. So high voltage Schering bridge is used to measure the capacitance of the capacitor. Capacitor means now the dielectric is capacitive in nature. So this high voltage Schering bridge is used to measure the capacitance, unknown capacitance or the capacitance of the dielectric, then dissipation factor or the loss factor tan delta, then dielectric loss angle, that is delta, and the relative permittivity or the dielectric constant. So you can see this is the high voltage Schering bridge. Now the four arms of the bridge consist of what? C1. C1 is nothing but unknown capacitance whose value is to be determined. So unknown capacitance means the capacitance of the dielectric, then which is connected in series with R1. Now this C2 is nothing but loss free capacitor, or it is also called standard capacitor. Then R3 is non-inductive resistor. Then the variable capacitor C4 is connected in parallel with the variable non-inductive resistor. Then the AC voltage, the high voltage AC voltage is applied between the points A and C. And the vibration detector, detector is also called what? The vibration galvanometer, which is connected between the points B and D. Then so you can see now, according to the theory of AC bridges, what is the balance condition? So Z1 upon, so you can see this bridge, Z1 upon Z2, the valence condition Z1 upon Z2 is equal to Z3 upon Z4. That means Z1 Z4 is equal to Z2 Z3. So this is the valence condition, and if we put the values of impedances, so Z1 is equal to R1 plus 1 upon J omega C1, because C1 and R1 are connected in series. Z2 is equal to what? 1 upon J omega C2, Z3 is equal to R3, and Z4 is equal to, so actually the C4 and R4 are connected in parallel, and therefore we can write R4 upon 1 plus J omega C4 into R4, right? So if we simplify the equation, then equating the real and imaginary parts, and if we separate out, we'll get the value of R1. R1 is equal to R3 C4 upon C2, and C1. C1 is nothing but what? Unknown capacitance, or it is the capacitance of the dielectric or the insulation. So is equal to C2 R4 upon R3, and therefore we can calculate the value of tan delta. So from this figure you can see the tan delta is equal to what? R1 upon XC. So is equal to R1 upon 1 upon omega C1, and therefore we can write, so tan delta is equal to omega R1 C1, where omega is equal to 2 pi f, f is equal to frequency. And also tan delta, if we put the values of R1 and C1 in this equation, we will get the value of tan delta in terms of what? R4 and R3. So is equal to, if we put the values of omega, then R1 is equal to this R3 C4 divided by C2, and C1 is equal to C2 R4 divided by R3, and therefore the value of tan delta is equal to omega C4 R4. So in this way we can determine, or we can find the value of tan delta. Tan delta means loss factor or dissipation factor, so is equal to omega R1 C1 or omega R4 C4. Then how to calculate the relative permittivity or the dielectric constant? So now the unknown capacitance, that is the capacitance of the dielectric, is known. So you can you know that C is equal to epsilon D divided by so the relative permittivity epsilon r is equal to relative permittivity, so it is equal to C into D divided by epsilon 0 into A, where epsilon 0 is equal to permittivity for the free space and C is equal to the capacitance of the dielectric, and D is equal to spacing between the electrodes, and between the electrodes the dielectric or the insulating material is there, and C is equal to capacitance of the dielectric. So we can calculate the value of dielectric constant by using this equation. So in this way we can calculate or we can find the value of tan delta, then dielectric constant, that is relative permittivity of the dielectric epsilon r, and the capacitance of the dielectric by using high voltage Schering bridge. Now coming to the case study or the example on Schering bridge. So a Schering bridge was used to determine the dielectric constant and the loss factor of 1 mm thick bakelite sheet at 50 years. Means this is dielectric which is between the two electrodes using a parallel plate electrode configuration. So electrode effective area is 100 centimeter square. Under balance condition, the bridge arms AB means test object, AD standard capacitor. Standard capacitor means C2, and CD variable capacitor means C4, 50 nanofarad is given. Then variable resistor R4 is equal to 1000 divided by pi ohm, and non-inductive resistor means what, R3, so is equal to 62 ohm. Now we have to find out the dielectric constant and dielectric loss factor tan delta. So how to calculate? So by using the equation C1 is equal to, we already discussed C1 is equal to C2 R4 divided by R3. Now the C2, that is standard capacitor 100 picofarad is given, then the variable non-inductive resistor, that is 1000 divided by pi ohm is given, and the R3 is also given, and therefore we can calculate the value of C1, that is nothing but the unknown capacitance or the capacitance of the bakelite sheet is equal to 513 microfarad. And then how to calculate the dielectric constant, that we already discussed. The epsilon r is equal to C1D divided by epsilon 0 into A. So if we put the values, we can calculate the value of relative permittivity or the dielectric constant is equal to 5.79. And finally, how to calculate the value of tan delta, that is the loss factor, dielectric loss factor. It is also called dissipation factor. So by using the equation, tan delta is equal to either omega C1R1 or omega C4R4. The values of C4 and R4 are given, and therefore if we put the values, we can calculate the value of tan delta, that is 0.005. So for good insulating materials, the value of tan delta should be between 0.001 to 0.0001. So in this way we can calculate the unknown capacitance, dielectric constant, and the tan delta means the dissipation factor or the loss factor. So this is about what non-inductive testing and the high voltage Schering bridge, and this chapter is the last chapter of this subject, high voltage engineering. Thank you very much.